everybody. Welcome to the National Air and Space Museum and to the Moving Beyond Earth Gallery, and especially to our What's New in Aerospace. It's our monthly activity that we have special late-breaking or especially exciting programs to offer you, or people to offer you, as we have today, who are absolutely fascinating in the knowledge they bring here about the sun. I'd like first to thank the Boeing Aerospace Corporation for making this program, What's New in Aerospace, possible. Those of you who've come through the Milestones of Flight Gallery know that they are responsible for that really marvelous redo, and we're looking forward to much more. Well, today we're celebrating the 10th anniversary of NASA's Stereo mission, appreciated worldwide as our solar system's space weather watchdog. Over the next 90 minutes, we'll have 4 dramatic TED-type talks by noted solar scientists and by an astronaut and former NASA Associate Administrator who has spent more hours exposed in space as he was doing his spacewalks as Hubble's chief Hubble hugger. Our first speaker will be Barbara J. Thompson, over there. She's a solar physicist at the NASA Goddard Space Flight Center in their Sciences and Exploration Directorate. And she'll be discussing the importance of a new perspective of seeing the sun in 3D, 3 dimensions. Then, 5-time shuttle astronaut and former NASA Associate Administrator John Mace Grunsfeld will discuss why, with space weather, what doesn't kill you makes you stronger, you hope. He'll then be followed by Janet G. Luhman, Senior Fellow at Space Sciences Laboratory at Berkeley, and a Stereo mission principal investigator, who will talk about solar impact on other planets, comets, and asteroids. And finally, we'll hear from the space weather woman, Tamitha Skov, a research scientist at the Aerospace Corporation, who will discuss using Stereo to do real-time forecasting of space weather, here, out there, and everywhere. And after that, I'll moderate a panel discussion, and we'll have Q&A. Hopefully, take those notes, and there'll be time to ask particularly inspiring and thought-provoking questions. That's what we're hoping for today. But first, to introduce us all to Stereo and to provide a welcome from the present NASA Associate Administrator, I'd like to hand it over to Lika. Lika Guha-Thakurta is Stereo Program Scientist, NASA Science Mission Directorate. Lika.
Thank you. Thank you, David, and thank you, Air and Space Museum, for hosting this event jointly with NASA, and of course to all of you audience who will make this a lively, fun event. But before I give my overview, it's my great honor and privilege to introduce our very new NASA Associate Administrator for Science, Dr. Thomas Zurbuchen, who is actually a card-carrying heliophysicist. And to drive this point home, heliophysics wasn't even a discipline one solar cycle ago. Thomas very much regrets not being here in person to participate in this event. He's away, but what he did is the next best thing. He has provided us with a video welcome address for all of you, and I'd like to play that for you and share it in his own words.
Hi, I'm Thomas Zurbuchen, and I have the honor of being recently named the Associate Administrator for the Science Mission Directorate at NASA headquarters in Washington. I wish I could be there with you today, not only as a heliophysicist to hear today's presentations firsthand, but as someone whose many goals in my new job is to share as widely as possible to the public the many aspects and vital work taking place in the heliophysics community. Heliophysics missions help us study what drives eruptions on the sun and how they travel outwards into space. In addition to examining how the space environment changes closer to home and affects our technological society, the other planets in our solar system, and the vast expanse of the universe. Understanding is great. Interconnected space systems help us better protect our astronauts and our robotic missions, as you will hear today, as we venture forth to our journey to Mars. And with missions to the solar systems and beyond. This is an exciting time for heliophysics, with upcoming missions in both the near and long term that represent the whole community, missions that demonstrate new technologies and enhance international collaborations, study emissions from the sun, and also up to the Earth's outer atmosphere. In addition to a spacecraft launching in 2018 that will get up close and personal with the sun as never before. With the many aspects of space weather, which you will also hear about today, the importance is so great that a new executive order signed by the President will ensure that federal agencies continue to work together collaboratively and help protect the Earth from the effects of hazardous solar emissions on our atmosphere and the technological society in space and on the ground. And of course, we await the upcoming solar eclipse in August 2017 that will cross our nation. It is indeed an inspiring time for the heliophysics community. I want to send a happy birthday shout out to the Stereo mission and its extended team. Over the past 10 years since Stereo launched, tremendous strides have been made in the heliophysics field, studying not only the sun, but also the impact it has on the entire space environment. Lastly, I want to remind everybody that while hardware makes these scientific accomplishments possible, it's the talented people inspired and dedicated that study the data and share the findings with the public worldwide and help develop and protect humanity's future and inspire the next generation of explorers. Enjoy today's presentations. NASA science drives some of the greatest explorations we have seen in human history, and just as early seafarers needed to map out the seas and understand their environment, their storms, before they could travel safely, we need to understand our neighbor as we explore further and further from home. Thank you.
Wow, that was pretty comprehensive heliophysics 101, right? In 3 minutes. I don't have to say a lot, actually. And what you're going to hear, many of the threads that Thomas mentions in his speech will be addressed by our expert panel members. And so just to get started, I'd kind of acquaint you a little bit with Sun 360. To do that, I would like you to actually put on your red and blue glasses. I will do the same, but I will take it off while you keep it on to see what is being showed there. And so what you're seeing there, of course, we are celebrating 10-year anniversary of Stereo mission, the mission that can be credited with giving us the first 360 view of the sun. That is all of the sun, the front side and the far side that impacts the entire solar system, not just our planet. And that mission was accomplished not just by NASA and US scientists, but a very large team of international scientists, and I want to give a shout out to them. Now, Stereo just didn't give us a 360 view around the sun, of the sun, but it did much, much more. What it did is it has actually given us a stereoscopic view, a 3D view. Imagine seeing a star kind of with depth in 3 dimensions. And if I can have the large screen movie showed at this point so you can have a better view of this 3-dimensional object, the sun. This is a movie that was created from 2 different perspectives of the Stereo spacecraft, about 2 to 3 degrees separated, so you get the depth perception. You can see the dark region, which are coronal holes where fast solar wind originates, and you're going to hear a lot more about that. And so what this mission has done is really given us not only a view, but a new understanding of the connectedness of active regions, of magnetic field canopy all around the sun. Let me go to our, oh, I'm sorry. I think, yeah, if you can please go back to the original slide so that I can show the next set of slides. And so what you are looking at here essentially is that stereo has kind of opened up a world for us, a 360 world. On the top left-hand corner is the simulation of a sun and a coronal mass ejection lifting off from the surface of the sun. This can be up to 10 billion tons of matter blasted into space. Solar storm has such magnitude and such spread that even tiny comet Encke's tail cannot withstand that wrath. And what you're seeing there is that coronal mass ejection literally ripping off comet's tail. And you're going to hear more about this. This is not a mechanical pressure exerted by coronal mass ejection, but actually a magnetic phenomenon known as magnetic reconnection. On the top right-hand corner, what you see is the invisible cloak, our magnetosphere, that is actually quivering under the solar radiation and particle streams. And this is the magnetosphere that actually protects our planet from harmful radiations. Every once in a while, of course, particles do manage to seep in to the magnetosphere, which then produces beautiful northern and southern light shows called the aurora borealis and australis, and that picture is taken from space station. And again, you're going to hear more details about both the beautiful manifestation of auroras, but also the harmful conditions that can be posed by coronal mass ejections and other solar transients. And so what we have been able to do in the last 10 years is utilizing the observations from the two different perspectives of stereo. With Solar Dynamics Observatory in space, with SOHO, we have been able to utilize observations, theory modeling, data analysis, high-end computing, and then with the international wide research community, we have created models, and we are continuing to create them, that gives us a perspective of coronal mass ejection blowing out into the solar system, all the way to the edge of the solar system. These models are housed at Community Coordinated Modeling Center at NASA's Goddard Space Flight Center, which is an interagency cooperation. People can put in their models, scientists, and can use it as well. And something of note here is that NASA's role here is to really provide understanding for space weather, collect observations for space weather, while NOAA really does the real-time forecasting of space weather for the entire nation. And you know what else we are doing? We can now take those models that we have created for our planet and begin to apply it in different worlds. And you'll see examples of that on Mars from Janet's talk. This gives you a picture of an exoplanetary world. So colleagues from SAO, for Cohen and his team, have created an interaction between a red dwarf planet and its exoplanet. And what you find here, very interesting, it's a model, is that the red dwarf star is actually stripping off the planetary environment of its exoplanet, rendering life inhabitable. So it gives us an insight into what is going to be a habitable planet. And so finally, on a personal note, I want to come back to 360, and it is the life of a program scientist 360. I came to NASA headquarters a long time ago to implement stereo mission. 18 years later, here I am actually celebrating the 10th anniversary of this mission, the tremendous science achievement, and the host of new generation heliophysicists that have been trained by this mission. And interestingly enough, our new AA, Thomas, is not here because he is actually present at the defense of his graduate student at University of Michigan, who is working on a very new concept of extended solar energetic particle events into the solar system, a very important phenomenon for space weather. So that is how, life goes around as well, I suppose. With that, I think I'd like to ask Barbara Thompson to come and give us really a full detailed view of the Sun 360.
Hi. I'm Barbara Thompson. I'm a solar physicist at NASA Goddard Space Flight Center. The story of the stereo mission started centuries ago with the regular observation of the sun and the likes of Galileo and Kepler. Patient observers were able to track sunspots as they transited the disk of the sun and noticed that they were transient in nature. They wondered what happened to those sunspots as they rotated out of the field of view. Perhaps they were the first people who dreamt of a solar stereo mission. Sometimes there were many sunspots and sometimes there were few. The sun has seasons, commonly known as the solar cycle or the sunspot cycle. A solar cycle has an average of 11 years, and over the years, with each of these solar cycles, the humanity advanced technologically. Eventually, radio and telegraphs were invented, and some began to notice that when there were more sunspots, there was more trouble with their equipment. But few anticipated the cosmic battle ignited by these deceptively simple sunspots. The only clue we had regarding the extended atmosphere of the sun was revealed during brief periods of solar eclipse. Millions across North America will be able to experience this spectacular phenomenon this coming August 21st, 2017. Get ready for the great North American eclipse. These benign-looking sunspots were the site of powerful magnetic fields extending from the solar interior into the sun's atmosphere, or corona. With the advent of space observations, we did not have to wait for brief periods provided by an eclipse to get a snapshot of the sun's atmosphere. We were able to image the corona over extended periods and witness the extraordinary dynamics of our nearest star. Solar flares look so much more interesting in an image from space. This is an extreme ultraviolet image, and you can see these eruptions and flares happening on a regular basis as the sun rotates. Every change, every aberration on the sun is due to its magnetic field. And that magnetic field extends far beyond sunspots, far beyond the normal visible sun, to fill the void in space between the planets, beyond Earth, far beyond even Pluto, creating the heliosphere. The solar wind is a steady stream from the sun, punctuated by huge eruptions of material and magnetic field. These eruptions, coronal mass ejections, drive space weather impacts throughout the heliosphere. Over time, humanity has become more dependent on technology that was in turn becoming increasingly vulnerable to the effects of space weather. But we also harness that technology to study the sun, understand space storms, and mitigate the effects of space weather. Generations of observations from the viewpoint of Earth had left us curious about several things. There were some clear puzzles. Phenomena that would sometimes appear one way, but sometimes would appear another way. Perhaps you've had the experience of riding in a car and suddenly experiencing a downpour of rain. Perhaps you've wondered, gee, did I just drive into the downpour? Or was it raining already and I drove into it? Or did it start raining? It's difficult to tell if you're just one person. But if you have a friend driving in a different car half a mile ahead of you, they would help you answer that question. They would tell if it suddenly started raining everywhere, or if it was raining and you drove into that rain. Their observations may be different from yours, but it doesn't make your own observation incorrect. What it does is that it adds context and perspective, and it gives you a richer understanding of your own experience. Prior to stereo, we knew that there were problems that could be solved with an additional observational vantage point, but we also anticipated that there were some surprises awaiting us. Phenomena that we thought we understood, but would prove to be more complex with added information. This video is a great example of how your mind comes to a natural yet incorrect conclusion. The little dinosaur appears to turn its head to follow you everywhere you go. However, as you view the far side of the dinosaur, you realize that it's an illusion and that your initial conclusion was wrong. The brain is a funny thing, though, because as soon as you move back to the front side, you think the dinosaur's head is moving again. Oops. Let's go back to my... For several years now, I've had this duplicitous little creature in my office as a reminder for me and my colleagues of two very important things. One, keep things in perspective. And two, more data is always a good thing. Even if you think you fully understand something, additional information can add richness and deeper understanding. I have some templates back there if you'd like a little buddy of your own to remind you of the importance of perspective. And there's also online, these are available online, as well as some other 3D templates if you'd like to make some other of these things. So that's where we were 10 years ago. We were aware of many mysteries on the sun and heliosphere that could only be unlocked with a new multi-viewpoint mission. And we were also fairly confident that there would be new surprises, new paradoxes that had yet to reveal themselves, known unknowns and unknown unknowns. And so the Stereo mission was born, an international consortium of researchers designing suites of cutting-edge instrumentation to study our dynamic sun and heliosphere as never before. 10 years ago, with the launch of Stereo, we experienced the power of perspective. This is a video constructed from real solar observations, the 3D sun made possible by Stereo. A number of members in this audience made this video possible. Stereo's one spacecraft moving ahead of Earth, one moving behind, gradually increasing in separation and expanding our view. As the imagers begin to glimpse the far side of the sun, other instruments were sensing the solar wind and inner heliosphere, reconstructing not only our beautiful star, but its extended atmosphere in which we live. This is a video of the far side of the sun, the other side of Earth, as we finally closed the gap on Sun 360. We had to wait years for it, and I don't think I'll ever tire of seeing it. This was quite an exciting moment. Stereo has allowed us the full perspective, unraveling old mysteries, as well as unlocking new puzzles for generations of researchers to come. In addition to the 360 sun and heliosphere, 10 years of observations has also allowed us to observe the sun's variation over much of a solar cycle. Magnetic fields emerging from those extremely innocuous sunspots are strongest during the peak of the solar cycle, or solar maximum. This coincides with a peak of eruptions and flares and space weather impacts, but has also provided insight into the sun's quiet periods, or solar minimum. It turns out that the sun is never truly quiet, but simply quiet by comparison. And it turns out that there are space weather phenomena even at the very dead of solar minimum. So that's the story of Stereo, a story of space and time, of context and perspective. How the sun went from a remote object with these seemingly innocuous sunspots to an interconnected, complex and dynamic system extending the 93 million miles to Earth and far beyond. The story of generations of effort culminating in a cutting-edge suite of instrumentation that capture how the sun's influence extends far beyond the surface, beyond Mercury, beyond Venus, and finally bringing us back home. And so this is the perfect point to hand off to our next speaker, John Grunsfeld, who knows better than anybody what it's like to live in the extended atmosphere of our beautiful yet tempestuous star.
Well, thank you very much, Barbara. It's really a pleasure to be here, and it is a great segue to move from our closest star, the sun, back to here on Earth. Now, I've spent most of my life trying to get off of the Earth, and I've had the privilege to go into space 5 times aboard various space shuttles, including 3 times to the Hubble Space Telescope. We can see directly the impacts of the sun on the Earth because we have this wonderful atmosphere, and the Earth has a wonderful magnetic field that protects us from the harmful effects of space weather most of the time, charged particles, electromagnetic waves, X-rays, gamma rays, and we can see that very vividly from the space station looking down of the aurora. And it's a beautiful representation of those particles, charged particles, energetic solar particles hitting the upper atmosphere, being absorbed, which is what protects us here on the ground, and we can observe that in these wonderful, beautiful colors. But as I said, this is a view from the space station looking down. That means as astronauts, we're up there where the charged particles are, where the effects of the sun, where the effect of cosmic rays can hit us. So in fact, we are, as astronauts, human cosmic ray detectors. Now, inside of the space shuttle or inside of the space station, we're relatively well protected, but outside in a spacesuit doing a spacewalk, in a cloth suit, just a few thin layers, we're pretty much exposed to all of those charged particles. Even inside the space shuttle, one night, I woke up in the middle of the night, and because we're going around the Earth once every 96 minutes, I was wearing eye shades, so my eyes were well dark adapted. I remember waking up in the middle of the night and seeing a light show, but I had my eye shades on. And it was the charged particles going through my eyeballs, creating little sparks of light. And it was fascinating to watch. I couldn't go back to sleep. I was so fascinated by knowing that these were mostly protons going through my eyeballs, and occasionally maybe a higher energy cosmic ray or a higher mass like a carbon or an oxygen traveling nearly the speed of light, zipping through my head, zipping through the space shuttle, all of us on board. And it wasn't a frightening thought at all. It was a beautiful thought. But it's radiation. It can be harmful. So I thought I would talk a little bit about that. So what are the risks to humans going out into space? Well, of course, you've all heard about many of the risks just because you're in free fall. You don't have gravity pulling down on your muscles and your bones. Fluid shifts. You see astronauts with big heads sometimes because the fluid is being pushed up towards the head. But you've heard about bone loss, about muscle loss, lack of cardiovascular tone, and these kind of things. Most of those effects have been countered by, and this is a big NASA secret, diet and exercise. And in fact, that's absolutely true. We now on the space station have state-of-the-art exercise equipment to simulate weightlifting that stresses our bones, that causes the bones to respond and muscles by getting stronger. We have treadmills and bicycles to keep our cardiovascular system strong. And with diet, that's increased the ability of our bodies to repair the things that happen in space. The distance from Earth, if there's a medical problem, well, the farther away you are, the harder it is to get medical care, so we'll have to take that with us. Of course, if you're inside of your spaceship and there's a fire or a leak or something, that could be harmful. Isolation and confinement, we've had lots of experiments, and some people don't like being in a really cramped space for a long period of time and get claustrophobic. But all of those things can be solved by technical means now. But the space radiation is one that's a really big question for us now, and I'll come back to that at the end. So what is the space radiation challenge? We can separate the space radiation challenge into kind of two components, one of which is that caused by the sun, and the other is by galactic cosmic rays. And in our galaxy, and in fact through the universe, there are atoms flying around in space at nearly the speed of light. And they make their way all the way in from the area between stars and from other stars in our galaxy all the way into the solar system and hit the Earth. In fact, that was my doctoral thesis work, was looking at those cosmic rays. And then there's the cosmic rays, the solar energetic particles that are emitted by our sun. And they're different in character. So the questions we're trying to ask from the scientific perspective and for the effects on human are, what are the different levels of cosmic rays? How do they vary over time? We've heard from Barbara that there's a solar cycle every 11 years. There's a modulation in the solar output, and the same is true for the radiation. We can see that in the particles. How much radiation will we have inside the spacecraft? How much during a spacewalk? What are the health risks associated with that? We know if you really bombard somebody with a lot of radiation in a very short period of time, like in a few seconds, you can easily kill somebody. But if you spread that radiation out over weeks or years, that same total dose might not be harmful at all. So what happens when you get too much radiation? Well, if you get too much radiation, it can increase your chance of getting cancer because it breaks the DNA, can cause mutations that can cause cells to go wild and create cancer. If you get too much, you can get acute effects, where, for instance, if it affects the blood-forming organs in your body that they shut down, then you can start to have immediate problems. You can have degenerative tissue effects where the radiation is just slowly breaking down tissues and the body doesn't have a chance to respond. And we've also seen, again, on ground studies, that if you give somebody too much radiation, it can affect your brain and nerve cells. And so all of these are bad things. But we don't know what the effects are spread out over long periods of time yet. So we're doing a lot of research into this. And that's part of the work that's being done on the International Space Station. But again, the Earth is surrounded by this very nice atmosphere, and even on the space station or at the Hubble Space Telescope, the Earth's magnetic field, that shields us. But of course, in the 1960s and 70s, we went beyond the Earth to the moon. This is John Young and Charlie Duke on the surface of the moon doing a spacewalk.
From the landing site in search for geological samples.
And here we go.
I hope you all think that looks like fun.
Would take them about 1 kilometer west of the landing site. They would make 2 stops to collect samples and conduct experiments.
You have 10529 in your flight plan.
But it couldn't pick a better spot. John, you're just beautiful. That is the most beautiful sight.
I think so too.
You're standing there on the rim of that crater.
Young used a portable instrument to measure the local magnetic field. He would later record the most intense magnetic field ever found on the moon, far higher than scientists ever suspected.
So spaceflight is inherently risky. This is not for the faint of heart. And the risk can be categorized in various big bins. There's the risk of blowing up in the rocket. It's a controlled explosion. There's the risk of burning up in the atmosphere when you come back to the Earth. And then there's all the risks when you're in space. Charlie Duke and John Young are out in a vacuum. People asked me for most of my young life, John, what, do you work in a vacuum? And now I get to say, yes, I do work in a vacuum. And people can't survive in a vacuum. And then, of course, as I said, the radiation can be a problem. So there's all kinds of things that, frankly, can kill you when you're in space. John Young and Charlie Duke, they were riding on the Saturn V rocket. That was a big rocket, a lot of stored energy. And all of the Apollo astronauts that went to the moon. They're on the surface of the moon. If their rocket didn't start back up when it was time to come home, they would have been stranded on the moon. And of course, the sun could have done one of these spectacular explosions, a coronal mass ejection that could have sent radiation their way. And we were very lucky during the Apollo program because those bad things didn't happen, and they got to go and do science on the moon. We sent our astronauts to the moon, as you just saw, to put out scientific experiments, to make observations, to collect geological samples, to come back. And I think that's what makes it worth risking our lives as astronauts, is to go out and push the frontiers of knowledge, to do great science. But just a few months after John Young and Charlie Duke were on the moon, and just a few months before Gene Cernan and Jack Schmitt walked on the moon on the final Apollo 17, in August of 1972, there was one of those pesky sunspots, and it kept producing little eruptions, and then a very large coronal mass ejection that sent a large proton, this is the nucleus of a hydrogen atom, towards the moon, that had we had our astronauts on the moon at the time, would have given them a very high dose of radiation. Would it have killed them? Probably not, but we would have wanted to get them back to Earth really quickly so they could get state-of-the-art medical treatment, which in 1972, not quite as good as today, but it could have been quite serious for those astronauts. And so there are real dangers due to solar events, and the key is to be able to observe the sun, predict them, and give warning to astronauts so they're not out in their spacesuits, they're at least inside of the spaceship. And we want to go further than the moon. We want to go to Mars. And this is a picture of Mars taken from the Hubble Space Telescope. I always use my talks as an excuse to show a Hubble image. And this picture shows you that Mars is very much like Earth. It has an atmosphere. You can see clouds in the atmosphere. But it's a very thin atmosphere. It's not enough to stop galactic cosmic rays or protons from very large solar events. And its magnetic field died away billions of years ago. So it doesn't have that protective envelope, and we'll hear more about that. The point is that when we talk about space weather, it's not just about the Earth and the sun, it's about our whole solar system. It's interplanetary. This is a plot showing our dynamical solar system with the sun. You can see Mercury, Venus, Earth, Mars, even Jupiter out there. And these solar events propagate all the way out until, in fact, they hit interstellar space. And our Intrepid Voyager spacecraft are observing that now. So we have a plan that looks at all of these risks of going to Mars. And a big part of it is environmental modeling, monitoring, and prediction of solar flares and solar events. To do that, it's not quite as advanced as terrestrial weather now, where we can see a hurricane and we can try and predict its path and we know where it will go. The sun is much more complicated. So there's a lot of knowledge that we still need to gain. And it's spacecraft like Stereo and all of our other spacecraft that are observing the sun that are going to give us the answers that we need. Even spacecraft that are around other planets, like the MAVEN spacecraft that you'll hear about. But also shielding and understanding human physiology. Even on our Mars rovers, we've put radiation detectors, and they've told us about not only the radiation on the surface of Mars, but also the radiation on the trip to Mars. And this is the good news part of the story, is the radiation assessment detector has shown us that the radiation that we'll get on a trip to Mars and living on the surface of Mars, now hopefully we're living underground or with shelter, but that trip is only going to provide a little more radiation than we get currently by living on the International Space Station. So this is a little bit technical, but we can ask the question, okay, how much more risk? Now, all of you came down to DC today, and I'll bet none of you thought about the risk of driving on the Beltway, or even being on the metro. Metro has been having its problems lately, or crossing the street that some rogue driver is going to run you over. But those are real risks as well. We're human beings. We have disease, we have traffic in DC and other things. So there's always risk. Well, we can compute those risks, and in fact, what's the risk from getting a induced death due to radiation on a trip to Mars? So this is a reference mission, 900 days. Takes you 6 months to get to Mars. You spend hundreds of days on the surface, and then it takes you 8 or 9 months to get back. So a 900-day total mission. That's a very long mission, but this bounds it. And it looks like there's only about a 4 to 6% or up to 10% additional risk due to radiation. So that's the good news. Now, how does that compare to other risks? Well, if you don't go to Mars and you live to be, in your 80s, you have about a 16% risk of dying from cancer in your lifetime. That's just a statistic. If you go to Mars and come back, your total risk goes up to 20%. Now, how many of you would be willing to take that risk, going 16 to 20%, if you got to go to Mars? It's a small additional risk. Now, right now, our rules don't allow us to do that, but I think we certainly can. So the key is that we need ALARA, not alarmed, as low as reasonably achievable. So I think we can go to Mars today. We have the technology, and I think our human physiology, remember, diet and exercise, will allow us to keep those bad effects of spaceflight from killing us. But we need to have a good network of spacecraft for advanced warning. We should have some good shielding, and we already do that. We should design a shelter as part of the habitat. So if there's a really big solar storm, you can hide out in a small area for a few days. I think we'll want to live under the Mars surface, where the dirt will protect us. You want to go fast on the way there to minimize your exposure. And we're going to have to accept a little bit more risk, because there are lots of things. The rocket can blow up, you can get hit by radiation, you can burn up, your rocket may not start on the way back. The radiation is just one part of that risk. And to be able to manage that risk, I call it helio teamwork. Helio meaning the sun and teamwork, of course, we have a group called the Space Radiation Analysis Group in Houston. They're always watching over, seeing what the sun is doing, talking to folks from NOAA, the National Oceanographic and Atmospheric Administration, that's responsible for space weather forecasting at a place called the Space Environment Center, Space Weather Prediction Center, sorry, that's an old slide, Boulder, Colorado. And they work together in real time and pre-flight to look at what dose we'll get. This is the pre-flight dose calculation for my mission, STS-103, my first Hubble mission, and they predict what it will be before we go, so we know what kind of risk we're taking. So I think managing the risk in exploration due to solar events will depend on our knowledge of space weather, but it will not stop us from going. And this is Konstantin Tsiolkovsky, a famous Russian rocket imaginer and designer. And I'll just read it. Man will not always stay on Earth. The pursuit of light and space will lead him to penetrate the bounds of the atmosphere, timidly at first, but in the end to conquer the whole of solar space. Now, I don't know about conquer, but certainly we will voyage out and explore the cosmos. And as we go further out from Earth, we're talking more and more about interplanetary space weather. And so to tell you more about that, I'd like to bring Janet up to the stage. Janet?
Thank you, Tom. So I had the great privilege in my job at the Berkeley Space Sciences Laboratory of being part of the Stereo mission. And that has really been an eye-opener in many ways. First off, it gives you a great perspective on what the universe that we live in and where we are and how small we are. We know the solar system formed about 4.5 billion years ago, and at the time the sun was part of the action, but there were all kinds of solid bodies flying around, accreting to form the planets and their moons. And so space weather was integrated into this whole scene, but it wasn't so distinct. Today, you might look in the sky and see a plain yellow disk of the sun, but anyone who works on stereo looks in the sky and sees this. So we have a different way of looking at the sun now, given all these imaging tools that we have had above the atmosphere and looking from different angles. The sun has a personality, and it has created a lot of weather phenomena that we've been studying over the years to understand better what our space environment is like and how it impacts us and the planets. So stereo pictures here include, on the upper right, there's a snowstorm created in the CCD cameras on stereo, which is analogous to the flashes of light that John saw in his eyes on the space station when an energetic particle storm happened. Stereo also captures the planets. In the central image, you see an image from the coronagraph on stereo, where many planets are visible, as well as some constellations. So we always have to be reminded, as we see these things sailing past the sun, that we live in this solar system, and there are other planets out there experiencing the same variety of activity that the sun puts out. And of course, there's the coronal mass ejections that you've heard about that create the space weather storms. So comets have taught us a lot about space weather from the very beginning. The image of Comet Encke up on the left is used again and again to illustrate the fact that even though you can't see something, it doesn't mean it doesn't have a great effect on you, although you see what looks like a gust of wind coming by Comet Encke as it orbits the sun. So the comet's atmosphere is in the first place produced by sunlight evaporating the ices of the comet, but then the coronal mass ejection comes by and rips that atmosphere off. So it giveth and the sun giveth and taketh away. And the comet, of course, is the ultimate solar windsock and doesn't fully represent all we know from the planets. The planets, in fact, have a variety of personalities, the Earth being one that has a magnetic field bubble around it, the Earth's magnetosphere, which was mentioned earlier. And the magnetic field bubble protects the atmosphere, which is buried deep inside of it. This is not to scale. The Earth is actually much smaller. And the lower right image tells you that the polar cap of the Earth is in fact swamped by the entry of energetic particles, not necessarily from outside in the solar wind and interplanetary space, but also from the magnetosphere itself, because they've been energized and dumped into the polar regions where the aurora can be seen. So what we know is that all of this energy that's striking the Earth's magnetosphere, even though it isn't a direct impact such as the comet has, is still producing a lot of energization of Earth's upper atmosphere. And as you will hear, there are many practical impacts from that deposition of energy in the Earth's atmosphere. We also see auroras at planets. The Earth is in the upper left, but Jupiter and Saturn here have auroral ovals of their own, and their auroral ovals also respond to the space weather in their vicinity. So because they have magnetic fields and the Earth has a magnetic field, we can make comparisons between these various bodies of the solar system and understand better how these processes produce auroras and what they do to the atmospheres of these planets, including our own. But for planets like Mars, which has been mentioned by John, where we're probably going next as a human population, species, there is no magnetic protection. Mars is out there in the solar wind and interplanetary space just like a comet. The solar wind and coronal mass ejections interact directly with Mars and, in fact, remove its atmosphere. The MAVEN mission is a new mission, relatively speaking, that's been going around Mars for over a year now. And what we see on the MAVEN mission is illustrated by the cartoon on the upper left, where the solar wind has come in and interacted directly with Mars' atmosphere and is ripping off the upper atmosphere of Mars. So you can imagine this has been occurring for billions of years. And so Mars has been constantly losing material to interplanetary space because of this comet-like impact on Mars' atmosphere, and also the occasional passage of coronal mass ejections that enhance that loss to space. So it's good to think about how lucky we are here on Earth, Earth being in the middle, of course, in that our neighboring terrestrial planets, which are in the habitable zone, may have once had oceans and substantial atmospheres like our own, but have ended up being a very inhospitable pair of planets, relatively speaking. And the question is, did Earth's magnetic field play a role in protecting it from this space weather scavenging of the upper atmosphere? And that's still very much a question in debate. But we know for sure that our neighboring planets don't have magnetic fields, and they also have atmospheres that are very different from Earth and lack critical components such as water. So that's an exciting area of research in heliophysics also. Now, because we have MAVEN mission in orbit around Mars, and MAVEN mission is instrumented to measure space weather, we can see what space weather is like at Mars and combine it with the information we have from the STEREO spacecraft and NEARER spacecraft to get a whole heliosphere view, basically, of space weather and where it's coming from and how it's impacting different places in the solar system. So the STEREO mission has really allowed us to have a very big picture of space weather. It's no longer confined to the Earth's location in the solar system, and that's going to be critical if we ever do visit Mars someday. So this is just an example of the kind of observations we obtain on STEREO. You can think of these squiggly lines here in the 3 panels as a Geiger counter trace showing how many counts you're getting per second at each of the locations of the STEREO spacecraft as well as at the Earth. And you can see that this solar energetic particle event produces very different Geiger counting rates at the different locations surrounding the sun. And this is the kind of information we have on a regular basis when stereo is fully operating and we have the near-Earth monitor like ACE. So space weather matters not just for Earth. It's probably played a role in the way the planets evolved over time, in particular their atmospheres. And we're working very hard to understand both the details of the physics of how space weather is affecting the various kinds of planetary environments and what the consequences are and will be in the future. And we are very lucky because you, as a citizen scientist, can get involved in watching space weather just by going to the internet these days. There is a host of things to see and watch that tell you what space weather is like today and also give you the information about how space weather works and is interconnected. But we also have a space weather reporter. And Tamitha Skov is here to introduce herself and hopefully her regular video programs so that you in fact can follow the story of space weather through time.
Or possibly be part of it. Thank you, Janet. Wonderful talk. Hi there. I don't know if you, if any of you know me, but my name is Tamitha Skov, and I am also known as the Space Weather Woman. For about the past 3 years or so, I've been doing space weather video forecasts. I see a couple people nodding. Wow, thank you. I will start just immediately by saying, did anybody catch the solar storm last week? There was aurora in Rochester, New York. There was aurora in Cape Cod. No? Wonder why. Didn't you see broadcast on the 7 o'clock news? No? No? Well, you will. This is all going to change very, very soon. So I am basically one of the first space weather, well, I probably am the first space weather broadcast meteorologist. We've been doing forecasting for a very long time, but it's not something that hits the 7 o'clock news because nobody really knows about it yet. But we're going to change that. This stuff affects everybody every single day. And who does it affect? Well, these are some of the space weather stakeholders that are affected by it right now. Notice that most of these people are on the ground, just like you. These are not astronauts, these are not cosmonauts, these are not people flying off to Mars or to interstellar space or sitting behind the sun. They're right here at home. And that's what really matters. Anybody here happen to be a ham radio operator? Amateur radio operator? Oh, John, of course you are. You're an astronaut. Anybody else? You guys are on the front lines? Absolutely. You guys are on the front lines of space weather. You know it hits you all the time. It affects everything you do. That's part of the emergency communications. Basically, when we have an earthquake and all communications is killed and dropped out, we have the Red Cross flying in ham radio ops to be able to provide the only communication, the only lifeline for these people in these really hard-hit places. They need to know what the space weather is doing in order to be able to communicate because it's do or die. Emergency Maritime Mobile Service Net. This is the backup for anybody who's at sea. Again, ham radio ops. Okay. Anybody happen to have one of these? Does anyone know what this is? Right? Yeah. Anybody ever use a GPS on one of these? Yeah? You guys belong in that top group there. See Fitbit, see the tractors, see the cars. GPS, believe it or not, is affected by space weather. You guys probably, when you go, what does my GPS do? What is it? What? I'm not over there. That's in the lake. That kind of thing can sometimes happen from space weather. And you guys are getting used to these drones flying around that are operated by GPS. That single frequency GPS, it's basically a cell phone brain being strapped onto a drone, onto these 50-pound monsters that fly around. They think this is going to pilot it for them? No, we got a lot to learn. The Google cars are a little bit different. They're better. They got LiDAR and maps and all these things to kind of help navigate. But these drones, how do you map the sky, right? So that's something we're working on. We also have space tourism. We got astronauts out there who are trying to take beautiful pictures. John knows firsthand, taking beautiful pictures for you guys so you can see some gorgeous aurora from the top down. We also have aurora tourists looking up, taking beautiful pictures from the bottom up. We've got a friend of mine who proposed to his wife up there on the screen under a beautifully aurora-lit sky. We also have airline flights. Anybody ever fly in a plane? Yeah? Okay, well, I'm just checking. You guys belong to that class there. Did you guys know that airline pilots are considered radiation workers? Did you guys know that? Some of their crew is not, and they should be. What about frequent flyers? Do you guys think you fly as much as a pilot does? Right? Do you think that radiation that John was talking about, and those guys, did you know that astronauts are also radiation workers? Did you know some of that radiation penetrates to the upper atmosphere? And if you sit in a balloon about 100,000 feet, which is higher than most planes fly, but it's still in our atmosphere, that's what the atmosphere is going to be like. That's what's going to be like on the ground for Mars astronauts. When they're down on the ground, it's going to be like being at the Earth at 100,000 feet. Lots of radiation. So we have to be smart about this. We need to become aware of this, not be scared. It's not that big a deal, but it is important. We can't ignore it. So space weather is here, and it affects us all the time. So I've heard everybody's talked about solar flares, solar storms, also known as coronal mass ejections. I will tell you how they affect Earth. Solar flares basically are just a bright flash of stuff that comes off of the sun. It's mostly light, but it affects things like radio waves, basically X-rays all the way down to radio waves. Things travel at the speed of light. They go very, very fast. It'll cause a radio communications blackout like ham radio and GPS issues for about maybe an hour, maybe a little bit more. Coronal mass ejections, which are what you're seeing on the right-hand side, those are much slower. They're massive amounts, like belching from the sun. They move very, very slowly, but if you can see there's magnetic field in them, that's why they look like a yo-yo. You can actually see kind of a loop that moves out. These things are so big, they actually go, they're actually about a quarter of the distance between the Earth and the sun. That's how wide they are by the time they hit Earth. So for these things to fly over us, it takes literally about 2 days. So we will be in what we call a solar storm situation for 2 days. Those massive things are what cause the aurora, and they cause all sorts of other things, just like solar flares do. Now, solar radiation storms, that's down at the bottom. I don't have a movie for that. And that solar radiation storm, you can't really see, you don't really see the effects. It's basically the effect of a solar flare and a coronal mass ejection. These are those energetic particles we were talking about. And as you can see, that's a map of the Earth. And you don't have to interpret the map, but just know that red is bad. Okay? So as you can see, that affects the upper atmosphere quite a bit. So those are the things that cause issues, and if I can get this thing to actually advance. Okay, so you can actually get all that data, by the way, if you want, from the Space Weather Prediction Center, NOAA. They are the ones that provide all the official data for civilians, for the military, for all of us. And there's a couple plots here a plot that shows all of this data. I don't want you to interpret the plot. Don't worry about that. Just letting you know that it's there. But here's the trick about space weather. It never happens as just one event. Usually there's a big sunspot that comes on the sun, on the Earth's facing part of the disk, and it's mad. And it just spits stuff off over and over and over and over. And it takes about 2 weeks for this nasty thing to rotate off of the Earth-facing disk. So what happens is it fires these storms at you. Flare, and then a CME, and then another flare, and then you get a particle storm coming with it. And it just is an onslaught that just overpowers Earth's defenses to a great degree. And that's what you're looking at. Here you're seeing on the bottom part of this, you see a couple spikes. Those are solar flares. Along with them, you've got two of the two big humps up the top that look like big camel humps. Those are radiation storms. So this one set of storms, this is a week period from January 23rd in 2012 to January 30th, the end of that week. You had 2 radio blackouts that caused ham radio and communications disruptions for over an hour, and 2 radiation storms, as well as a big coronal mass ejection that caused aurora for days. So you could be out of commission for about a week, very easily. Now, what does that mean? Well, let's talk about some of the effects of this. So the first top panel, I'm going to show you, talk about communication disruptions. Remember that one of the flares I showed you? That was what we call an X2 flare. It caused what's called a R3. NOAA has scales for these things. It doesn't mean all that much, but an R3 class radio blackout. That's a moderate blackout. Now here's what happened. You see that, notice that big red spot in the top left panel, it's kind of covering all of the Western Hemisphere. Can you kind of see that in the map, hopefully? That's basically the United States plus all of South America. And the FAA reported that the Radio Communications Center for the Central East Pacific and the Central West Pacific regions, they were, quote, impacted severely by solar activity between 1830 Zulu time and 1930 Zulu time on the 27th of January due to the R3 solar flare radio blackout. 13 requests were received from air traffic control for overdue position reports, unquote. Translation? They lost track of 13 commercial airliners. They just couldn't talk to them, period. For maybe an hour, maybe half an hour. Now, there are mitigating things that the FAA does to be able to handle these types of situations. They've been doing it for decades. But nonetheless, this happens, especially during solar minimum. Now, the radiation storm that ensued a few days, well, actually a couple days prior to that, that's all that red stuff. This is in the right top plot. It's all that red stuff up at the poles. Radiation storms affect the poles. You have stuff that comes in and it kind of comes at the poles, like the head, the top, and the bottom of the Earth is kind of exposed. So they get a lot more penetration. Now, this stuff also affects GPS and it also affects communications. Right? So what happens here is that now that gas is so expensive, the airlines are suffering too. They actually have planes that fly over the poles. And they want to do it more often because it saves gas. But the problem is, that storm right there caused, for 3 nights in a row, major airlines to lose position reports from their airplanes. Not all of them, but some of them. And they would have intermittent comm issues. They didn't know when, they didn't know how long, it would just happen. And this kind of stuff happens all the time that we have these solar storms. So they become issues. Now again, GPS signal disruptions. I was talking about that. If you look off to the right, and I'm showing you just on the left-hand side, I'm just showing you some of the people that use it. And we're talking precision farmers, tractors. John Deere, for instance, calls NOAA all the time and says, why do we have all our GPS technicians having to go out during a solar storm? They're driving us crazy because our GPS tractors can't get locks. We're stuck. So NOAA helps John Deere and a whole bunch of other contractors all the time with these types of things. But here's an example. That plot on the very far right, the one with the white and it's all blue, it shows the United States basically on, what is it, October 19th. Actually, it was my birthday, believe it or not. It shows it pretty good. The GPS position error is about 5 meters. It's not great, but it's not too bad. The plot on the left shows during a solar storm, a big storm back in 2001 in April. See the difference? Huge difference. So GPS can go wonky during a solar storm and nobody knows why, right? Or at least the public doesn't know why. We know why, but these are things that we have to correct. So that's what a typical solar storm does. But what about a superstorm? What about the big ones that hit? Well, we have a standard candle. We call it the March 6th event from 1989. This was an X15 flare. Remember, I just showed you what an X2 flare can do. This is an X15, and this is on the same scale. It's a Richter scale. Same kind of thing. It's a logarithmic scale. So an X15 has got 8 more zeros behind it than a X2, right? Or more than that, 13 more zeros. So when the X15, it was followed by a solar storm, meaning a CME. The weather satellites lost images for hours. Okay? We had TDRS, the TDRS-1 ComSat, as a military ComSat, had 250 anomalies. The Space Shuttle Discovery fuel sensor failed. We had the Hydro-Quebec system shut down. The James Bay network was offline for 9 hours. There were 6 million people without power. It caused the Toronto stock market to close. They couldn't do anything. There was brilliant aurora as far south as Texas and Florida. And you can see there's burned transformers. You can see the pictures in there. Those are actually melted transformers because these big solar storms will actually cause currents to be induced in the ground, which then cause currents to be induced in the power lines, which then will overload the transformers and they melt. Now these storms are not that common. This is like once every 25 to 50 years, so don't worry about it. And believe it or not, there are even bigger storms than that. I won't even talk about those, but that's what the policymakers in Washington, the Lloyds of London report, Carrington event, all the fear-mongering comes with the super storms. But those are so rare and almost ridiculous to even think about from the point of view of what we can do to mitigate these things, that we don't really want to talk about that type of stuff. It's just not practical. But we are trying to do stuff. We are trying to get better at what we do. So really, when we kind of look at it, where are we when it comes to forecasting, and why does it matter? Well, back in the 1960s, terrestrial weather forecasting was really pretty much just starting out. You had Harry Volkmann, actually. He was a broadcast meteorologist, and he was the one who made the first the first on-the-air tornado warning. Maybe some of you might remember Harry. He was a great guy. He actually took a military base of weather forecasts and a tornado warning and decided to broadcast it on the air. Now, what was funny about that was that a lot of people were very afraid it was going to incite panic in the public. But instead, the public were so grateful. They sent him something like 1,600 letters of encouragement and thank you, we're so glad you're on the job. Thank you for giving us the information that we need to be able to make smart choices. And that's kind of where we are today with space weather. It's not something that's panicking people. This is something where people are really appreciating this information. They want to become spacefaring. You know, you heard Thomas Zurbuchen at the very beginning of all this talk about sailing the seas of space. Well, that's really where we are. We are beginning to sail the seas of space, and we need to understand that the boundaries between us and the space really don't exist. The weather is the same, it's just a little further up. So, you may not know that there's a solar storm going on right now, and the storm I talked about where there was the aurora in Rochester was occurring just last week. I'll show you part of the space weather forecast that I did that was forecasting this aurora coming, so the aurora photographers and the ham radio ops would all know that this thing was coming and would cause some problems. So let me give you an example. The sun's activity has really picked up this week, starting with a massive solar storm that pretty much evacuated the whole eastern side of the disk, but you couldn't see it from Earth. Thank God for stereo, our backside monitor. It caught it from the side. This solar storm has now hit Earth and has wreaked havoc. We've had aurora pretty much all over the world for the last 12 hours or so. And we're now going to be dealing with some fast wind from this massive coronal hole right here. It's beginning to move into the Earth strike zone. So hot on its heels, we're going to have yet a chance for more storming. So if you ever wonder why we have a backside monitor, here is why. This is the coronagraph from Stereo A. It allows us to see these big solar storms being launched and launched out towards Earth. And you can see this monster being launched right here. It takes up almost the entire side of the disk all the way out like that. We couldn't see this thing from the Earth vantage point, but here it shows it and it's on its way to Earth, and thank goodness for stereo, otherwise we would have never seen this latest solar storm coming. So getting back to that point, this is why it's so important that we look at the sun from all different sides. It's all about perspective, as Barbara mentioned earlier. And it's all about being able to have eyes on every side of the sun we possibly can, to be able to give us, our astronauts and our people here on the ground, the warning that they need to be able to take action, to either go out and enjoy the storm or get down off their rig and don't worry about whether or not they can't get any communications with their antennas. Okay, just if I can move forward. Okay, here we go. So what I wanted to show you is just a couple examples of some recent solar storms. You know, we had one, actually between these two, we're having one right now. We had one on the 13th, we had one at the beginning of October, we had one in August. I mean, we have these things all the time, and you don't have to go to Iceland, you don't have to go to Greenland to be able to see aurora. They happen right here at home. So we've got some from Rochester. These are all been what I call field reporters. I am so humbled by these people who go out and chase aurora and then report them on social media so we know right when it's happening and where it's happening so that other people can join in the fun. So we got pictures from Rochester and Hartford, Wisconsin. That's how far it came down just from that weak solar storm I was telling you about in that forecast. And then we had some in the 3rd of August from Sheridan, Wyoming, and even Paradox Valley, Colorado. So some of you actually sit in the aurora zone right now. You could probably just on a dark night step outside your backyard. If you know when and where to look, step outside your backyard and just look up at the skies or look at the northern horizon. You'd be amazed at what you see. So what I just gave you is kind of the Earth version of space weather. And this was all NOAA's purview. But let me talk a little bit about NASA's purview. This is now the future of space weather forecasting. And this is where we actually start branching out and looking at other planets. Now, any of you seen a movie, you know, it's kind of a small little low-budget movie called The Martian? Anybody familiar with that one? Yeah? Oh, yeah, I watched it too. I just barely caught it. I mean, who knows why I even heard of it. It was just kind of this, yeah. I'm just a rabid fan of Matt Damon, I guess. But, you know, we're actually living the precursor to that movie right now because we have a rover, Curiosity, that's been, you know, kind of rambling around out there on Mars, enjoying life and tweeting and talking about it and really giving us a fantastic data, but also kind of keeping us connected to everything that's going on that planet. But back on the March 7th of 2013, there was a big solar storm that was approaching Mars. And NASA decided to shut Curiosity down due to this approaching solar storm, basically trying to safe it and keep it okay while it weathered this particle radiation. Now imagine, you know, and as a matter of fact, Curiosity actually tweeted saying, "There's a storm a-coming. There's a solar storm heading for Mars. I'm going back to sleep to weather it out." because there aren't any bunkers. It can't dig a hole and sit under there. So it just kind of shut down and just waited. But imagine if this weren't just curiosity. Imagine Matt Damon sitting up there petting his little rover, right? And they're weathering the storm out together. Kind of puts a whole new spin on The Martian, doesn't it? So what would a space weather forecast look like? Well, I actually did one. Now, switching away from Earth, we're going to move to another favorite planet, and that's Mars. In order to do that, though, we need our backside monitor, Stereo B. You can see here's Earth, here's the Sun, and here's Stereo B staring at the Sun from behind relative to Earth. But you notice Mars is pretty close to Stereo B, so they've almost got exactly the same view. And why that's important is what's happened recently is, bam, do you see that right there? That is a huge solar storm that's launched. It's now Mars directed, and we have to worry about that thing hitting Mars and causing problems for astronauts and the rovers and all of the equipment there on that planet. If we switch to the coronagraph view just to verify, bam, do you see that right there? That's a huge halo around the Sun. That means that solar storm is coming toward Mars, directly aimed at it. So we're going to have to do a lot of prep work to make sure everybody's safe. Switching to our prediction model, Enlil, we've actually run this model into the future to get an idea of when this storm is actually going to hit Mars. So this is a view from the Sun's north pole. You can see it right here. Here's Earth over here, and here's Mars over here. Stereo B sits right there. That's the blue satellite. Now when this thing launches, bam, do you see how big this thing is? It spreads all the way past Stereo B and actually does hit Mars. We expect the impact to be starting around the 8th and probably storming into the 9th. Now this is a very fast solar storm, so there will be radiation involved. So you astronauts on Mars, you're going to need to go into your bunkers starting around the 8th and keep monitoring your radiation levels until things begin to quiet down. But if things quiet down fast enough, then you might actually get a chance to see some UV aurora. Could you imagine that? Being an astronaut, being Matt Damon, and getting in your rover and checking your radiation monitor and going, okay, well, I guess I'm all right. I can come out of the ground now. And then stepping up onto the planet and putting on your UV glasses, kind of like our 3D glasses, and looking out at the vista and just seeing aurora everywhere. Would that be cool? That'd be pretty cool, huh? And especially if, you know, if this is really far in the future, but imagine if Earth and Mars were aligned and he'd be on the phone going, yeah, hun, in about 2 days, you're going to see the most amazing aurora because that storm's going to hit Earth after it hits Mars. Would that be cool? I mean, I don't know about you, but that's a pretty cool future to me. So, what can I say? Our future is relying on space, right? We've got Google cars, we've got drones, even Amazon. Have you seen Amazon Prime? Amazon Prime Air? They're hiring right now. There are 21 open, in case anybody's looking for a job, there are 21 open positions with Amazon Prime right now where you can either fly drones or create software to help deliver packages right to your doorstep using GPS-enabled drones. So space weather is becoming more important all the time. And not only that, but we have space tourism that's coming in right here. We've got a company called Worldview that plans to have new space tourism balloons, helium balloons, that will be flying just the average person, you and me, up into these balloons and let us witness the aurora all around us. Now, I don't know about you, but I would love to see the aurora, but I don't want to go up when there's a radiation storm. I'll leave that to the astronauts. You can have it, John. I'm going to stay down here. I don't want fireworks in my eyes with my eyes closed. No, thank you. I'm good. Unless I wear Kevlar or something. But this is coming. You know when they plan to have the first manned flights? 2017. I don't know about you, but I think that's next year, right? So it's here. Space weather is here. The future is here. And are we prepared? Well, the best way to prepare is to be aware. So broadcast meteorology, space meteorology is coming, and hopefully you will embrace it, as so many other have, because space weather is like the weather in your own backyard. It's just a little further up. Thank you.
Well, thank you very much. Thank you very much, Tamitha. I'd like to bring up all the speakers now. Lika, John, Barbara, Tamitha, you're here, and Janet. And there should be time for some questions. If you have questions in the audience, please go to the microphone right there. And I understand we have some questions on social media. First, I always like to give precedence to people who actually come here, and so if there's anyone with a question, you're more than welcome to stand up there. And when I see you up there, I will ask you to state your questions succinctly. But I'd like to start with a quick question. Stereo seems to be very unique in looking at the sun from two directions, but it's, as a space mission, it's not permanent and it has a lifetime. What are you going to do after stereo to keep this predictive modeling active and helpful? And I can ask anyone. You start with Lika.
I'll start off. Like with anything else, we do these observations to really get to the science and understanding. So with stereo to perspective, we actually got a pretty good handle on what is the 3D morphology of a coronal mass ejection. So if we had only one perspective, now we can fold in that three-dimensional model in order to do a better prediction. But that's not a good enough answer. I think for future, and I'm not now going to speak as a NASA program manager, but as a scientist and a dreamer, what I think we could envision is, with the advances in small spacecraft, in miniaturized instrumentation, I'd like to see the entire solar system populated with these small spacecraft with instrumentation, ensemble of them. Call them heliophysics ensemble. It's not for just heliophysics science, it's for all of us.
This would be like Themis?
This is not like Themis. This is actually distributed approach. You could have a population of spacecraft, orbiting around Mars. Mars is L1, L2, L3, or any other planet we go to, and of course as a pearl of string around our sun. Up, down, sideways.
Any thoughts? Yeah, John.
Just worth mentioning that we do have a constellation of satellites that are studying the sun and the environment between the sun and the Earth and the interplanetary space, all the way out to our Voyagers, in fact. Now, they're old spacecraft, but new spacecraft are coming online, and it was highlighted earlier. We have Solar Probe, which is going to be the spacecraft to go the closest to the sun ever. I mean, right in this dynamic corona. Where it's so hot, millions of degrees, and of course the secret is we're going to go at night. But that's how we survive the heat. I'm glad you all laughed. But this is going to be a fantastic mission launching October 2018, very advanced. But it's this suite of satellites that we have, the Advanced Composition Explorer. In collaboration with NOAA, we launched the Discover mission just a couple of years ago that lives between the Earth and the sun and is observing the sun and the Earth at the same time.
And these, I take it then, anything in space, either interplanetary or in high Earth orbit, can be valuable in this regard. So this is actually a good thing to realize. Any other thoughts? We have a questioner from the floor.
My question is what we as ordinary citizens can do to help our society be prepared for space weather events.
A lot of it depends upon where you live. There's lots of different places that you can, or there's lots of different ways you can get involved in terms of doing citizen science. But if you, for instance, are an aurora photographer, there's places that there's event, what are they called? Projects that, like Aurorasaurus, that have been led very, very successfully since 2012. And we're trying to actually map where the aurora is being seen relative to the United States or even in Europe. And we weren't able to do that without citizens. I mean, we actually call you people field reporters because you guys are actually out there in the field and keeping us abreast of what is going on. Because the science is still very, very new. As I mentioned, space weather is back where terrestrial weather was back in the 1960s. So it's just beginning. So there's so many different roles, and we could actually talk more about that offline.
Lika.
Actually, I would go to Eclipse 2017, which is kind of pretty close. In a year's time, the entire US will see some version of eclipse, but the totality goes from coast to coast from Oregon to South Carolina. And in that band of totality, you will be able to see the corona with your unaided eyes, basically, right? Because the moon blocks the visible disk of the sun. And that is a time where I would like to see that all of our citizens, especially these next generation citizens, get involved in documenting their experience, in taking pictures. Imagine the technology at our disposal today. This is going to be 90 minutes, at any spot, it's of the order of 2.5 minutes of totality, but a 90-minute path. So if, people like you can get your friends and others and start a movement. And this will also teach you more about not just solar physics, about the connection of the sun to our atmosphere, to our geospace environment, to other planets, or how we find exoplanets. There's just lots of important information that can be taught and passed on just around that one event.
Janet?
Yes, this is an example of your taxpayer dollars at work. So you are already helping. Of course, NASA's programs and all the other agency programs that do this kind of work compete with many other things. And so if you get involved in any way in politics, local or national, or in talking to your congressional representatives or state representatives, you might have neighborhood laboratories that do this kind of thing, a NASA center, or if you live in Boulder, Colorado, you've got everything in one place practically. You can use their outreach opportunities to bring them to the local schools, to make people aware of this kind of enterprise and both its interest and its usefulness to them as citizens and taxpayers, so that we have the kind of support that's necessary to maintain and grow this system and make people aware that there is more to weather than what we see in an everyday experience.
Thank you. Yes, and I think we have some questions from the ether.
Yes, we have some social media questions. The first is from Maximilian, who wants to understand why when we look at some of these stereo images, they are blue.
Because they are not invisible in the visible light spectrum. We have to color them something. And it's somewhat arbitrary, but we choose a color associated with the wavelength that we take the image in. We have imagers that view multiple wavelengths for various reasons. Some are colder, some are hotter, they show different things. And so because we're in the extreme ultraviolet, whenever we color code them, it helps us just to identify the images. If you like blue, you can look at the blue image. If you like red, you can look at the red image. But it's just for context. We could show them in black and white, they just don't look as fun.
And the best part is that, for much of our youth, what do our parents tell us? Don't look at the sun. Yeah. And what we're trying to tell you is with all these great spacecraft now, you can go on the web, there are apps you can look up. It's good to look at the sun, and we learn a lot from doing that. And the spacecraft can see the sun in light that our human eyes can't see. So we can look at the sun.
And I also want to add, there is a method to the madness. The other reason for that is because each one of these telescopes is looking at the sun in different wavelengths. It's looking at a different height in the atmosphere. And there's different things going on. So we'll have some type of science that's going on, some type of eruption that you can't really see in the blue sun. But then you go to the red sun and, boy, it just sticks out like a sore thumb. And it's like, oh, that's what's happening. So it helps us scientists kind of understand, almost like peeling the layers of an onion, which layer we need to be looking at to be able to determine exactly what phenomena that we need to study and what is exactly happening. But we can't, because it's just such a busy atmosphere, we can't see it all at once. I mean, if we were to try, it would be things all on top of each other. So this is one way that we can kind of peel the layers of the onion little bit by little bit and be able to pick out each thing very, very particularly to be able to study that one thing. And having it color-coded lets us immediately lock into, oh yeah, that's 131, or that's 304 angstroms. We know instinctively as scientists what part of that atmosphere, which layer of that onion we're looking at.
It is definitely not false, as some people might say. Well, we are out of time, and I want to thank everyone, the audience, for being here and for experiencing with us the fact that solar weather is with us every day, and we have to get more familiar with it. And thank you to our panel again, and I wish you a very good day, and thanks again to Boeing and to the National Air and Space Museum for hosting this program. Thank you very much.